Okay, so we've got y is equal to sine theta plus root 3 cos theta. So 1 squared is 1, root 3 squared is 3, 3 plus 1 is 4, square root of 4 is 2. Ding! Well, that's easy. And then phi is equal to tan to the minus 1, or the arctangent of root 3. It's obviously root 3 over 1. So just to be careful, the y value is root 3, which is about 1.2, something like that, and the x value is 1. So we're looking for an angle in there which is bigger than 45, but not much bigger than 45. So I'll bang that in my calculator on. So arc tangent of square root of 3 equals 1.05. So that is equal to 1.05. And just so you know, there's about 60 degrees in a radian, so that value there is about 60 degrees, which is sort of what we expected. So that's me doing a sort of on-the-fly sanity check. Okay, I do those as I go along. So that means we've now got our graph. Now, we now know that y is equal to 2 sine brackets theta plus 1.05. Right, now what I'd like to do is I'd like to show you what that actually means. So if I draw a sine wave, it starts at 0, it goes up to the amplitude, down to the negative amplitude, and then back up again. Okay, so that is, in this case, that would be 2. This value here would be minus 2, so down there is minus 2, and that's plus 2. But at the moment, we're an ordinary sine wave. We don't have a phase shift. Now let's think what happens when theta is equal to 0. When theta is equal to 0, we're going to calculate the sine of 1.05, aren't we? Now let me just remind you that this is 2 pi here, this is pi, and this under the peak there is pi over 2. And just to help, this is equal to 360 degrees, this is equal to 180 degrees, and this is equal to 90 degrees. Now that's 90, and we've just said that 1.05 is about 60 degrees, isn't it? So there's 90, we've got to come down a bit, so that value there is roughly 1.05 radians. So when theta is 0, the value of the curve is about 1.5, which means that I now need to move that graph to the left so that that point, the green point there, is on the axis. Okay, so what that's going to do is give me, let me just move that up a bit, that's going to make the curve, so we'll draw that again, it's going to look like this. Sorry about it being so wiggly and all. So it's going to look like that. So this value here, which is the value 1.05, is where it crosses the axis. This here is minus 1.05. That's my max there, which is plus 2. That's the min there, which is minus 2. So when theta is equal to 0, the value is the sine of 1.05, which is actually root 3, so it's 2 times root 3 is the value there. So let me be absolutely clear what we're saying here. So the amplitude is whatever r is, so that's easy. But if phi is greater than 0, move the graph, move sine to the left. And if phi is less than 0, move the sine curve to the right. Okay, so you're going to be asked this on your exam, just so you know, and it's worth 2 marks, and this is 2 really easy marks if you get this. So in this particular case, phi, the phase angle, was 1.05, so 1.05 is less than pi over 2. I'll do it in degrees, so 1.05 is about 60, the max there is 90, so I've just come down a bit, and you know, a third of the way if you like, and I've just moved the whole curve by that amount to the left. I mean, if your diagram is as poor as mine there, you'll still get the mark on the exam, because it shows that you know what's going on, even though it's not the most beautiful sine curve. Tell me if you've got that, or tell me if you don't get it. Ask questions at this point, because this is easy points if you understand what I'm talking about. Repeat it. Yeah, okay, Kevin, I'll do exactly that. And in fact, I'll rub that out and do it again. So, is this maths? Of course it's maths. Wouldn't be doing it if it wasn't maths.
Tom?
Yes?
An interesting question asked in the chat.
Yeah.
What is the goal of doing this?
Right, okay. The goal of doing this is all maths is good for you. But being less jokey, what we're doing here is basically waves. If you can build any vibration of any kind from waves. So generally speaking, if you were to take a violin playing a middle C, it wouldn't be what's the question asking? Right, so that's what I'm saying. So what is the purpose of doing the sine waves? If you take an impact, a hammer hitting a piece of metal, or a car hitting a pothole in the road, or a satellite crashing into an asteroid, or music that you're playing, somebody playing drums on a recording or something like that. All of these things basically come down to waves, and waves are sort of everywhere. The mechs are going to be using waves. The elects are going to be using waves. I don't know about the chems, I'm pretty sure the computer scientists aren't going to be using waves in quite the same way. But waves come into engineering in every place. But they don't come in nice and smoothly. They come in as very complicated waveforms. And what we're doing here is we're building up a waveform in pieces. So we're taking a sine wave and a cosine wave, and we're adding them together. Later on, we're going to be looking at how they behave, so attenuation and things like that. But the starting point is, can we add them together? So we've taken a sine wave and a cosine wave, and let me just pull up my spreadsheet. So we've got a spreadsheet here, and yeah, this was the sine of y is equal to sine theta plus the square root of cos theta. I'll pull up, just show you the spreadsheet. Okay, so here's the spreadsheet. There's the sine wave, so that's sine theta, and here's the cos theta. So it was the amplitude of the sine wave was 1. The amplitude of the cos wave was the square root of 3, sqrt of 3. Okay, so that's the square root of cos 3. So you can see that the amplitude of the combined wave, which is the grey one here, hits the axis at 2, which is what we've just calculated. And look at the cosine. You see, sorry, the combined wave. You see it's crossing there where the sine is 0, and it's going to start around here somewhere, isn't it? Which is the angle that we've just calculated, isn't it? So just follow that line down. It's going to be just a bit to the left of minus 1 radian, isn't it? And if we go back to our calculation, which is here, it's just going to be slightly less than 1 radian, which is what we've got there. So if I were to sketch this, first of all, let me sketch a vanilla sine wave. So I'll do this in blue. So here's a vanilla sine wave. Okay. So this is 2 pi, this is pi over 2, and this is also 360 degrees, this is 180 degrees, and this is 90 degrees. Okay, that's a vanilla sine wave. Now the easy bit here is to say that the amplitude is 2, so we could just say that that's 2 and that's minus 2, and actually you get a point for that. That wasn't hard. But there's something else going on, which is that when theta is equal to 0, we've got sine of 1.05. So looking at the graph, this point here is 90. So if I go about a third of the way in, that point there is going to be about 60. Okay, which means that that point needs to move to the x-axis. So the whole curve needs to move to the left by 60 degrees, or by a radian, which means that our final that our final sketch is going to look something like this. It's going to go up, and then down, and then up again. Okay, so this value here is minus 1.05 radians. This point here is going to be, let's try that again, this point here is going to be 2, and this point here is going to be minus 2. So the whole curve, you see the curve there has moved to the left, which is what was happening here. Let me draw it with a pen. So that bit there tells you how far your curve has got to move. So the whole curve has now moved to the left, which means that I've got a phase angle here, which is phi, and I've got an amplitude here, which is r. Okay, is that all right? And if I go back to the spreadsheet, you see I've got there, the amplitude is 2, and you can see that this line is going to come down here at minus 1.05. So that's where it's going to pass the axis. In fact, why don't I even show that? If I change that to 3 times that, I bet that will be enough. No, okay, 4 times that will be enough. Yeah, there we go. So this is where we're coming through the x-axis. So that's minus 1.05 radians, and that's the 60 degree there, and that's the combined wave that we're looking at. All right. So let's minimize that. What happens if it's less than 0? Yeah, good question, Haran. What happens if this is negative? So let me change my color. So if this is negative, then the curve moves to the right. So what you would get is a sine wave doing something like that. And then it would come through the axis like that. So if phi is positive, the graph moves to the left. So let me do that. Phi is greater than 0, move left. And if phi is less than 0, move right. Okay, that's what happens there. Right, I think we spent enough time on that. I'm a bit aware that there's some other stuff I need to do. Yes, I think Sarah's going to speak.
Kevin's dropped a question into the chat. What's the equation of the original graph, and what expression made it move by the amount you indicated? Could you just point that out on your whiteboard, please?
Okay.
Thank you.
Right. So what the original graph is here. Y is equal to sine theta plus root 3 cos theta. Then we've added them together to get this expression, which is rather scruffy now, which is 2 sine theta plus phi, and we calculated the value of phi, which is we calculated here. So let me write that here. So what we've shown is that that is equal to 2 sine brackets theta plus 1.05 in this particular case. Okay, so what I'm now plotting is the curve, this black line. Let me put a red, no, let's keep it black. So this black line, I'm just duplicating it because this will show on the video. So that black line is 2 sine theta plus 1.05. So the graph has moved to the left. Yeah. Okay, I'm going to leave it there because there's some other stuff I'd really like to get finished before we break. So what we've done, let's imagine we have a curve that's doing that. So we've got y is equal to r sine theta plus phi. Okay, so that's the graph that we've got there. But let's imagine we've got an equation of the form r sine theta plus phi is equal to 3, let's say. Okay, so what we would do then is we'd get the line 3, wherever that happens to be, and let's imagine that that's the line 3. So if we got an equation of the form r sine theta plus phi is equal to 3, the solutions are going to be there, and there, and there. Okay, so how do we find what they are? Well, a simple bit of algebra is the answer. Right, so what we're going to do is we're going to say r sine theta plus phi is equal to 3, so sine theta plus phi is equal to 3 over r. Okay, so I now take the arc sine of both sides, so theta plus phi is equal to sine to the minus 1 of 3 over r. We know what phi is, we've calculated that, so we can now say that theta is equal to sine to the minus 1 of 3 over r minus phi. Okay? So that means that we can find the values of theta where the line, in this case 3, is crossing the curve that we've got. Okay, so that's one kind of answer. What this could be, imagine this is the amplitude of some music playing into your earbuds, and that we've decided that 90 dB is perfectly high enough, so we set this to be 90 dB, let's say, for the sake of argument. Then what we can say is that if the signal, if the amplitude of the noise that's hitting your ears exceeds 90 dB, then just clip that off. And the same obviously at the bottom, you'd clip that off, so you can limit the amount of sound that's hitting somebody's ear. Okay, so you can make sure that whatever they're playing, you can. What's the y value again? So Richard, the y value is a line that I've just chosen at random, but if this sort of thing happens so many times, if this is the suspension on your car, you can say this is where it bottoms out because your wheels just can't travel far enough, so you put a dead stop on the suspension. So if the wheel has to travel further than that, you limit it. If it's acoustic, you can say greater than this will cause your permanent ear damage, so we'll clip the sound and not allow it to go higher than that. If it is something like the I don't know, the acceleration of a rocket, you can say you can't accelerate greater than that because it will destroy the rocket, so you clip the thrust on the rocket and don't allow it to go any further. There are so many different examples of these things. So at the moment I've just used 3 as an arbitrary constant, and actually if you look at the textbook it's written as C. I'll do this again then. Okay, let's say your car, so here's your car, and you can drive it at 300 miles per hour mph. However, the engine will be destroyed if you exceed 250 miles an hour. I'm sure you all drive at those kinds of speeds. Okay, so you don't really want to destroy your engine. So what you do is you have got the power output of your engine, and let's say for the sake of argument it's shaped something like that. This is 300 miles an hour, that's the equivalent of that, and this is minus 300 miles an hour. Okay, but what you want to do is say, I don't want it to go that fast because I don't want to destroy the engine, it costs me loads of money. So I'm going to draw a line sort of there and there, which is 250 miles an hour. That's the power output of the engine. So what you're actually saying is that I want to know where these points are so that I can make sure that I don't exceed those values. Okay, so what we're saying is that r sine theta plus phi is equal to some limit, which I'm just going to call C now. So it's some limit that is set by the conditions. So in this case I'm saying 250 miles an hour. It could be the amplitude of headphones, it could be the thrust of a rocket, it could be the rate of change of a chemical process. There are many different applications for this stuff. So what I'm saying is, can I find the values of theta where I'm hitting these values? So that's this value here, this value here, this one here, this one here. Can I find the values of theta that give me those values? So the answer is yes, you can. So the first thing I'm going to do is I'm going to divide this equation by r on both sides. So I get sine theta plus phi is equal to C over r. Okay, So then it's theta that I want. I know phi because I've already calculated that, or I've been given it in the question. I'll know c, and I've calculated r. So now what I can say is theta plus phi is equal to sine to the minus 1 of c over r, which is a constant divided by the amplitude. All right. Come here, mouse. So I'll move that up a bit. So I know what phi is. I'll have calculated that. I know what r is, and I know what c is. So I can say that theta is equal to sine to the minus 1 of c over r minus phi. Okay? And that gives me the values. I mean, most specifically, let's have a red pen. Hopefully that's the first value it'll give me, because obviously that value repeats every 2 pi, and then I need to find that value, but I'll go over that later. But again, that repeats every 2 pi, and these two values down here are related to those. So once you've got those, all of them fall into place. So basically, theta has an infinite number of answers, but I'm actually interested in the ones close to 0. Can I explain the car scenario? You get the algebra. Yeah. Okay, so what I was saying with a car is that this is the power output of your car. I did say the speed, but you could look at it as the power output of the engine of the car. So it could be, I mean, you can drive internal combustion engines faster than the components can go. So I used to know somebody who raced minis a long time ago, and what he found is that if he over revved his car, which he generally did in races, what would happen is one of the pistons, right, just so you know how cars work, let's have pistons are like that. They have a hole in them, and then they have something called a conrod, which has got a sort of curve like that, and then a round bit, and that's where that's the crank of the car. And obviously let's try and do that slightly more like a crank. So a crank would look like that, and then this thing rotates round like that. So that's going boom, and the car is driving along. What happened with his car is that this broke here and here, and when one broke, all 4 of them broke. So his bonnet would suddenly get 4 neat little holes across the bonnet, because all of the pistons had come flying out like you know, cruise missiles being fired from a submarine, and his car wouldn't work anymore because he's got 4 holes in the cylinder head. So obviously that's not something you want to happen to your car. All your pistons blow out of the car. So what you do is you put a limiter into it so it doesn't over rev. So what this is saying is I want to limit this process, whatever the process is, and I tell you this happens in mechanical engineering, in electronic engineering, in chemical engineering. It happens all over the place. So but the maths is the same, which is you need to put a limit to say I don't want to go above this level, because above this level damage occurs, let's say. So what you do is you have a constant c, which is the constant that I've put here, c. So we know the equation r sine theta plus phi. We've already dealt with that. We're saying that where does it equal that constant? Because if it's greater than that, I need to do something about it, which is to stop that or that. Okay? So what I'm saying is that, okay, we divide by r, we take the arc sine, we move the phi across to the other side, and we end up with this expression here, which says this is where trouble occurs. Okay? And once you've got that, then you can do something with it. But before you've found that out, then you can't. Right. I think I'm going to move on now because I'm aware that time is absolutely flying past us, and there is just one more thing that I need to do. I don't need to do that. Or that. No, okay, no, I can leave it there. Right, I think that's covered enough to deal with this tutorial. Right. Francis, I'm delighted when people ask questions because I know that you're thinking about it. Right, okay, so I've sort of gone over everything we need for trig functions. Just so you know, there will be a question on trig functions on your exam paper. and they'll be similar to the ones that are in the textbook, and the textbook is similar to ones that are in the tutorial. And I'm quite happy to go over those now, but if anybody wants to go now, that's fine. I'm not going to get mad with anybody, but I will now go through a couple of the examples in the textbook, and just so you know, they're not dissimilar to the ones in the tutorial. Okay, so I guess all the thank yous are people who are off, so I'll give them a second or two. And I'm going to go through these rather than ask you to go through them, because I'm aware that time is flying. I don't know if Tim and Philip are still here, but last week apparently the PAL session was cancelled, but you didn't get to hear about it, so you did show up. So I'm really sorry about that. I've asked why we didn't get to hear about it, but there is a PAL session today. Ashley will be there doing last week's material, so if you have the time you could go along to that today, and obviously there'll be a PAL session next week. Yeah, sorry Philip, that's my fault. I changed the nav bar and I just lost the PALs. I'll put them back on this afternoon, but they're not there this minute, but they will be back this afternoon. Yeah, it is on today, Tim. Yeah, that's okay. All right, so what I'll do now is question 5 on the tutorial sheet. What we've got is we're looking for sine theta minus cos theta is equal to minus 0.5, and we want the value of theta less than or equal to 0 and less than or equal to 2 pi. Theta needs to be between 0 and 2 pi, and that's the equation we're going to solve. So the first thing we need to do, we'll ignore the minus 0.5, we're just going to take this bit here and we're going to get that into the form r sine theta plus phi. Okay, so that's not really too hard to do. We're going to get r is equal to the square root of 1 squared plus 1 squared, obviously. So, oops. So r is equal to root 2, and phi is equal to tan to the minus 1 of minus 1 over 1. Okay, so let's just remind ourselves what that means. We'll do with a blue pen over here. So minus 1 in the y is there, and 1 in the x is there. So the angle is either going to be minus in degrees 45 or plus 273, 315, is it? It must be 315. So it's either that angle is a negative angle or that angle is a positive angle, and they're both the same. It doesn't really matter which you use. Okay, so that means that we're going to get that we've got root 2 sine brackets theta plus, and this is for actually not plus, is it? I'm going to use it minus, and that's going to be pi over 4. That's the angle here, and if you don't believe me, check it on your calculator. The reason is this is 1 and this is 1, so it's obviously a 45-degree angle, and a 45 degrees pi over 4, and that is going to equal minus 0.5. Okay, what we want is the value of theta in that range. That's what we're looking for. So we can say that sine theta minus pi over 4 is equal to minus 0.5 divided by root 2. Again, don't mess with your calculator until the very end. Leave that out. So we can say that, let's just move that up a bit. We can say that theta minus pi over 4 is equal to, keep wanting to do tans, so is equal to sine to the minus 1 of minus 0.5 divided by root 2. So theta is equal to sine to the minus 1 of minus 0.5 divided by root 2. minus pi over 4. Okay, so let's put that into a calculator. So we're going to get arc sine of minus 0.5 divided by squirt 2, close brackets, and I get that equal to minus 0.36, and from that I'm going to subtract, is that what somebody was bleeping me? No. Yeah, that is plus. So I'm going to say plus shift pi divide 4 equals, and I get that to be equal to 0.42. Okay, so then I'll drag this in here. I'm going to say 0.42, enter. Brilliant. It's because it's timed out. So redo that, go to the bottom, and it was question, this one, 0.42. Ta-da! And that's the value. Okay. The others are similar to this. They're going to carry on in that way. There was something else I wanted to do. Finding max and min position. Yeah, all right. So maybe I should do that, one of those as well. I will do one of those. So let me just show you about max and min position. So in this case, we've got the curve which is 4 sine theta plus 3 cos theta plus 3. So what that means is we've got, let me move that off the screen. I don't want you full screen. Let me move this up. So this is example 8.5. So we've got y, let's start with y is equal to 4 sine theta plus 3 cos theta. Okay, the question actually has a plus 3 on the end, but I'll just start with that for now. What we're going to get here is we're going to get that is equal to, I mean this is like the other ones that we've done. It's going to be 4 squared plus 3 squared, which is 25. So this is going to be 5 sine brackets theta plus, and this is going to be the arctan of 3 over 4, which I will just remind myself it's 0.64, isn't it? So shift arctan of 3 divide 4 equals 0.64. So that's 0.64. Okay, is everybody okay with that? You see where that came from? It's the example we've done before. So if I were to graph that, what I would get is 0.64. That's 36 degrees. So it's going to look something like that. Okay, so we've moved here 0.64 minus, so we've moved to the left 0.64, and the amplitude of that is 5. Okay, everybody see what I've done there? So that's the graph of 5 sine theta plus phi. Okay, so now what I'm going to do, because the question actually says that y is equal to, let me do this in blue, plus 3. So all that means is that I just pick up this curve and move it up 3. So that's 5. So I need to go up to 8. Okay, that's going to be the max. So it's going to be, okay, Francis, right, let me just undo this bit that I'm talking about here. So the 5 here is equal to the square root of 4 squared plus 3 squared. So no, don't worry. The only stupid question is the one you don't ask. So if you're not with it, you just ask the question every time. So what we've got here is 4 squared is 16, 3 squared is 9, 16 plus 9 is 25. So the square root of 25 is the 5 that we've got there. So that's where the 5 came from. And that's the R value, isn't it? Is that okay? And then the phi value there is the arctan of 3 over 4. So that's sort of where we started. Okay, let's take those away. But the question 8.5 is actually 4 sine theta plus 3 cos theta plus 3. Okay, so what I'm saying is that that means that we need to add 3 to every point on this curve. So it's going to start like that, and it's going to, so we add 3, that's minus 5. So the minimum value is going to be minus 2. The maximum value is going to be plus 8, isn't it? And so it's going to be a curve like that. So that's 5. So that distance there is 2, minus 2, sorry. And this max point up here is plus 8. So all I've done is I've taken the black curve, and every point on the curve I've added 3 to it, so it's gone up by 3. So the whole curve has been moved upwards. And for the electronics people, they would call that a DC value of 3. So you've got an alternating voltage or current or whatever, and you've got a DC value, so the whole thing is being uplifted by 3. Okay, and what we're interested in is finding the position of the maximum. Okay, yes, Philip, it's a DC offset. That's exactly what it is. So, just so we're clear, that we've done 3 things to these poor old sine waves. One is we've changed the amplitude. 2 is we've changed the phase. And 3 is we've given them a DC offset. So those are the 3 things that we've done to the curve. We could, but I'm not going to, change the frequency as well. But let's just stay with what we've got for now. So we've got the whole thing with a DC offset, and what I would like to know is here the position of the first maximum. Okay, so how are we going to find that? Well, the maximum value is, let me put, I'm still in blue, so here. So the maximum value of a sine is 1, isn't it? So the maximum value of 5 sine is obviously 5. So the maximum value of 5 sine plus 3 is 8. So the maximum value is 8. Okay, is that clear to everybody? The maximum value of a sine, yeah, thank you, Robin. The maximum value of a sine is 1. So the maximum value of 5 times the sine is 5. So the maximum value of 5 times the sine plus 3 is going to be 8. So can anybody tell me what the minimum value is going to be? Yeah, okay. Thomas, it's minus, of course. So the minimum value is going to be minus 1 for the sine, so that becomes minus 5. So 5 times minus 1 is minus 5. Minus 5 plus 3 means that we've got minus 2. Okay, that's the max and the minimum value, and you might be asked for either of those. So, the maximum value, let me just move my screen up a bit. The maximum value is at, where do you find the maximum value of a sine wave? Let's do a vanilla one. Yeah, what's the angle at its peak? Oh, okay, so this is 2 pi. This is pi. So what's that? Exactly. So this is pi over 2. So the maximum value is at pi over 2. So that is where theta plus phi equal pi over 2. Okay, so in this case we've got theta plus 0.64, yep, 64 is equal to pi over 2. Move that up a bit. Oops, So we've now got theta max is equal to pi over 2 minus 0.64, and that is going to equal 0.93 radians. Okay, so that is the position of the maximum value. So if I needed to know where that is, that's how I would find it. Now, if you had a graph that looked like this, and the question said what's the maximum value of the first positive value, and you calculated that one, so you got this answer to be negative, then all you would do is add 2 pi to the answer to get the value there. So if it says give the answer between 0 and 2 pi, which we did on this first one, so we said the answer between 0 and 2 pi, and you got a negative value, then you would just add 2 pi to it to move to the next wave, and then you'd find the next one. But if it said give the answer between pi less than or equal to theta less than or equal to pi, so you're going to have a range of 2 pi, because that's how often sinusoids repeat themselves, and the values will either be 0 to 2 pi, sorry, that was meant to be an arrow, 0 to 2 pi, or it'll be minus pi to plus pi. So it will just be a theta value between those things. Frequency, yeah, don't worry about frequency. We're not worrying about frequency. If the frequency was different, the theta is the frequency, isn't it? That's where the frequency is. So theta can have multiple values on this particular curve, but frequency, you've got a low frequency and then you've got a high frequency. That's the only difference. But I'm just taking one curve, so I'm not really worrying about that at the moment. I will later, because there are much easier techniques. Right, I think we've covered enough in one day, and I think you need a bit of time to assimilate this. So what I suggest you do is have a look at the you can look at the examples on the textbook, and you can have a look at the tutorial as well, but also draw some drawings. I mean, this spreadsheet that I gave you, you can put the values into that and you can see the answer there, can't you? The answers are actually there in front of you. So the one that we've just done was, what was it? Was it sine was 3? No, it's, okay, so the sine is 4 and the cos is 3. So there's the curve. That's exactly what we're looking for. Okay, and so if you built a spreadsheet like this, you can actually draw the things out and see what the curves look like. The blue line here is the sine wave, the orange one is the cosine wave, and the grey one there is the combined wave. And then I could add 3 to them and do all those sorts of things. Right, I'm going to stop and I'll answer any questions that anybody's got, and I suspect we might get some questions in the tutorial when we meet there. Okay, ciao Philip, see you next week. Anybody else? Any other questions? Okay, see you Thomas. Okay, cheers Francis, Alexander. These are the tough guys that have stayed to the end, aren't they? Alright, I'm going to stop the recording.